Okay, now we're ready to talk about these window functions again, which are going to be really important when we do analysis in the next unit, when we start to actually have the computer learn things about music automatically. There's just this thing we need to be aware of when we do the short time Fourier transform that can go a little bit wrong. So remember, because of this periodicity assumption, when I look at just a part of a signal, so if I'm doing my short time Fourier transform, I just take a window of it. I'm doing the DFT in that window, and the assumption is that that thing is perfectly periodic, so it actually repeats itself forever. The pitfall of doing this is if you get a signal that doesn't go through an integer number of periods of your window, and you take a chunk of it, well, the DFT assumes that it is infinitely periodic, so it's going to really look like this as it repeats itself. It ends up with this awkward jump, and you get all these bleeds and all this bleed into other frequencies. So the solution was to pre-multiply the signal by something called a window function, so scale it down. In this example, it was just half of a sine function. So this is showing like if I take that frequency and I window it and then multiply it by this window function, then I actually get the right frequency bins there. So I don't get all this frequency bleed. A similar thing happens with the square wave. If I take a window of the square wave, I erroneously think that it's got this one stretched period, but that's just because it's a continuation of the one before it. So that's not right. So I end up with all these extra frequencies. But if I window it and then multiply it by this window function, then I only get the frequencies that it really should be. It's like in between two frequencies at each harmonic. All right. So we saw window functions. But now I'm going to be able to explain this a little more, why the amplitudes look like they do. So if I go back and I look at the definition of the discrete Fourier transform and the definition of the inverse discrete Fourier transform, what I see is that they look very similar. They're both just these dot products with phasors. So it turns out, I showed you a moment ago that the discrete Fourier transform of the convolution of two things is the product of discrete Fourier transforms. You can actually show the same thing going the other way around because these equations are similar. This is why it's called duality. So what I can show, let me actually write it. So I'll say just as the DFT of the convolution of two signals is the product of those signals DFTs, the multiplication, or say the product of two signals is the convolution of the DFTs of the two signals. Okay, so let me say it this way. Let me put these on two lines next to each other. So the DFT of the convolution of two signals is the product of the signals DFT. That's what we saw. But also the product of the two signals is the convolution of the DFT. So what we say here is, I'll call this convolution in time domain, and I'll call this convolution in frequency domain. So we're going to look at this now, because that's what we were doing with the window function. We were multiplying a window by our signal, a window function by our signal. So we were multiplying, we're taking like the sine half of it and multiplying that by our signal. So we were doing that a moment ago in the frequency domain with the discrete Fourier transform. Now we're going to do it in the time domain, but what we'll see is that we actually get a convolution in the frequency domain. So let me show you, and now I'll be able to explain why windowing, I'll be able to explain another reason, like you can see it in the time domain here, but I'll be able to explain the frequency domain, why this is so bad, okay, and why you need a window function. So I'm going to look at just no window function, just like chopping the signal off, and I'm going to look at three other window functions: the hand window, the sine window, and the black window. Actually, the sine window is the first one I'll look at. Sine window, hand window, and something called Blackman-Harris, and I'll show you the progression here of how they get better and better in some regards, although there's some trade-offs. One of my professors in college said that choosing a window was like choosing a religion. They have different uses for different purposes. Okay, So let me make a signal that looks like this. So it's a square wave. And I'm going to window it. So let's say that I'm just going to take a chunk of it towards the middle and look at the Fourier transform of that. So let's first look at just the window that we call the square window. It's no window function at all. So it's like, here's the window, and then here's what I took. All right. So if I look at the Fourier transform of the original thing, I get this. If I look at the Fourier transform of this window function, which is just, again, just taking a chunk of it, not tapering it down at the ends at all. This is the Fourier transform. So what you see is, I mean, it kind of oscillates back and forth. It's got these teeth, but the teeth are all pretty high. So this is 10 cubed, this is 10 to the negative 12. So you see that there's a lot of bleed in the frequency response of this. So what it means is I'm actually taking the convolution of this with this to get this. So this is the convolution of this signal with this signal. So what you see is all these, they call them side lobes. You see that there's this frequency bleed because I'm actually, it's like I have an echo of this. I have many echoes actually of this thing. And I can kind of see them as these little ripples here. So I kind of see these all over the place. So that's not good. Okay. So that's one problem we see in the frequency domain. It causes all this bleed. So the convolution of this with this is this. Okay, because again, I'm multiplying things in the time domain, so I'm multiplying this by this, which means that it's actually convolution in the frequency domain. Okay. Let's use a slightly better window that actually tapers down at the ends. So here's the sine window, 1/2 of a sine. So here's the window, and here's what it looks like when I multiply these two together. So compared to the regular, we call it the square window, like not doing anything, just taking that little chunk. What we see is that, okay, yes, it still has a lot of side lobes, but they die away more quickly. They're just a little bit lower in amplitude. So let's see. So look here, I go from 10 cubed, and I never go below 1 there. Somewhere between 1 and 1,000. Actually, that's quite big. I'm probably around almost 10 or 100 the whole way through. Whereas here, I actually start to dip down below 1 as I go. So these side lobes are, again, remember I'm on a log scale. So this is actually, pretty different. So I still see some of these wiggles, but I don't see them as much. Okay. The other thing that's a little different, actually, is I can see that this one actually, if I zoom in a little bit, well, it's hard to see, but this one kind of lingers a little bit longer here. So it actually does a little bit of averaging. So it's like, if you have a bunch of echoes in sequence, that's an average. That's like the low-pass filter I showed. That's why this is a little bit wider than the other one. Okay. Now let's use what people consider to be a better window than the sine window. It's called a hand window. That's the one you'll be using in assignment 3. Because here's a hand window. It's actually just a sine squared. So you see that it tapers off a little faster at the ends. And actually now I'm starting to see a bigger difference here. I fall below 1 much sooner. You see how these side lobes fall out a lot more? They're much lower. And I can see the effect. The wiggles aren't as strong here. Okay, then there's one last window called the Blackman-Harris window. You can see how I defined it up here. It's actually the difference of 3 cosines in a constant. If I look at this, it's something that tapers off even faster. It's got a very particular shape. And now we really see, okay, these side lobes are very low. They're below 10 to the negative third most of the time here. So in terms of the side lobes, this one's the best. And here's the result. Look how smooth. Smooth as butter. Okay? The one downside of the Blackman-Harris window, there's really no perfect window. Okay? The one downside of the Blackman-Harris window is that, look, it does actually linger pretty long. Almost up to, I don't know, what's like, you can see that it kind of lingers up here until around 100, 150 hertz. What that means is it's going to blur things out a little bit at the beginning in a frequency nearby. That's why these peaks, if you look at all of them, these peaks are kind of the most spread out. So it makes the peaks in frequency wider than the other ones, but it has very low side lobes. So it's good for analysis because it makes things pop out a little more. It doesn't introduce these spurious peaks. You may mistake some of these peaks for being actual frequencies, but they're not. They're just, especially in the square window, you might think that some of these are actual frequencies, but they're not. They're just artifacts of the window. So anyway, I just wanted to talk about that because that is important. All right, so I'll have you summarize in your own words what the pros and cons of some of these windows are. Okay, just one more thing I want to go over.